Hello everybody, welcome to another episode of Math-321. So today we're going to finish up Investigation 26 and we're going to get started on Investigation 27. So let's finish up with Investigation 26 first. This was about cosets and Lagrange's theorem. So here's what we learned last time, the main points. So definition 26.3, let G be a group and H a subgroup of G. Let tilde H be the relation on G such that for all A, B in G, A is related to B by the tilde H relation, if and only if A inverse B is an element of H. So that was an important relation that we defined, and then we spent quite a bit of time talking about its equivalence classes. So we showed, in fact, that it is an equivalence relation, and then that meant that its equivalence classes, which are written like this, bracket A, and so this is just defined as everything in G that is equivalent to A under this relation. We showed that those form a partition of the group G. And then we had this definition of cosets, so definition 26.6. Let G be a group with subgroup H, and let little g be in big G. The left coset of H in G containing little g is the set little g H, which is equal to, basically you just multiply every element in the subgroup H by little g on the left. That's why it's called the left coset. And then the right coset of H in G containing little g is the set H little g, and that is exactly the same way, except that you take all of the elements in the subgroup H and you multiply little g on the right, so that's called the right coset. And then the element G itself, that is called the coset representative of GH or HG. And then we also showed that the equivalence classes of that tilde H relation, those are precisely the left cosets of H. In other words, if we have bracket A, that's the equivalence class of A under the tilde H relation, that is exactly the left coset where you just multiply A times everything in H. So let's get into Lagrange's theorem. So I'm going to go ahead and tell you what Lagrange's theorem is, and then we'll kind of build up to proving it. So you might have noticed by now that every finite group G and every subgroup H that we've encountered have had this property that the order of H, the number of elements in H, divides the number of elements in G. In fact, that is always the case, and that's a consequence of Lagrange's theorem. If you don't know Lagrange, he was quite a famous mathematician and astronomer from the late 1700s. There's quite a few things named after him. Anyway, this theorem, theorem 26.11, is called Lagrange's theorem, and it says if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. So this is what we were just talking about. It's something we've observed all along, and it's really one of the most important theorems in all of finite group theory. So throughout this section, we're going to stick with the convention that G will be a group of finite order, and then H is going to be a subgroup of G. And then we're also going to use this notation right here. Previously, we had only been using that for groups and subgroups, but we're going to use that for any finite set X to denote the number of elements that are in X. That's a pretty standard set notation for the number of elements in a set, so I hope you've seen it before. Okay, so we're going to start off with a preview activity to build up to that proof of Lagrange's theorem. So one of the things that we need to do for the proof is to figure out the number of elements that are in each left coset. So we're going to let A be an element of G, and then we're going to use a function. It's a very naturally defined function called phi, and phi is going to be a function from the left coset AH to the subgroup H, defined by this definition right here. So when you plug an element AH from that coset into phi, it just returns H. So go ahead and try these four parts here, and then we'll go over them on the next slide. Okay, so let's go over these answers here. So part A is by an injection. So the answer here is yes, and let's prove it. So I'm just going to do the proof the same way I do the proof of every injection. So I'm going to take two elements from the domain. I'll just call them x1 and x2, just like I always call them. And this is the domain here. And we're going to suppose that these give us the same output from the function. Okay, and then our job to prove that this is an injection is we will show that x1 has to equal x2. So that's just a standard way of proving an injection. Okay, so let's see what we get from our assumptions. So I'm going to start with this, this let statement right here. So just the very fact that x1 and x2 are elements of this left coset means something. So since x1 and x2 are in AH, that means that there exist two elements of H, which I'm just going to call H1 and H2. So there have to be two elements in H like that, such that x1 equals a H1 and x2 equals a H2. So we know that these two H's have to exist because otherwise x1 and x2 could not be in this left coset A capital H. Okay, so then what we have is that phi of AH1 equals phi of AH2. Okay, and so that tells us, based on the formula for what phi actually is, that tells us right there that H1 equals H2. So that's just applying the formula of phi, where you take away the A and you just leave the H part. So what does that mean? Well, if H1 equals H2, then AH1 equals AH2, so x1 equals x2. Okay, so we did that. So part B is phi a surjection. This is usually a little trickier to prove because it involves some scratch work, but I think in this case it's actually going to be pretty easy. So this is a yes. So for our proof here, the way I always do these is I just say let y be an element of the codomain. So here the codomain is H. And then what we need to do is we will show there exists some x in the domain. So in this case the domain is AH, such that phi of x equals y. Okay, so all right, so how are we going to do this? Well, if y is an element of H, so since y is an element of H, then the element that is in the domain that's going to give us this y as an output is going to be the following. It's going to be AY, and that is definitely going to be in AH, because AH is just all the elements of H multiplied by A on the left. So AY is definitely in AH, and then we just directly get, when we plug AY into the phi function, that just gives us y. Okay, so this is pretty easy. So that AY thing, that is your x. Okay. All right, so we did part A and part B. We showed it's an injection and a surjection. So yes, from part A and part B. Okay, so part D here. Part D is actually what we were trying to be able to get to. So what are our answers to parts A through C? Tell us about the number of elements in AH and the number of elements in H. So I hope that you remember this from your discrete structures class, that whenever there's a bijection between two sets, that means they have the same cardinality. So a bijection, I'll just write that down, a bijection between two sets means they have the same, I called it cardinality, but we could just call it order, the same order. So it means the same thing, just the number of elements. So the number of elements in H is the same as the number of elements in AH. So this is actually the key fact that is going to let us prove Lagrange's theorem. Okay, so in this activity we're going to go ahead and we're going to prove Lagrange's theorem, and it's actually really easy now that we have that last preview activity under our belt. And I just put it up there in the corner for you to look at. So go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go ahead and go over the activity here. So suppose G is partitioned into M distinct equivalence classes with representatives A1, A2, up through AM. Fill in the blanks to write G as a disjoint union of left cosets. So I think they may have actually meant to put left cosets here instead of equivalence classes, but I presume that the equivalence classes that they're talking about are those left cosets that are the equivalence classes under the tilde h operation. So anyway, here what we can do is we can write G is the union of these cosets, A1H, A2H, A3H, A4H, and dot dot dot, and all the way up through AMH. So in part B here, they're just reminding us that in preview activity 26.10, we found out that the number of elements in each left coset is the same as the number of elements in H. So this is telling us that, I'll call it AI for just the general A, is equal to H, order of H, for I equals 1 to dot 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 up through M. Okay, so all of those left cosets are exactly the same size as the set H. And then in part C here, you may have learned at some point that if x and y are disjoint finite sets, then the number of elements in the union of x and y is just the sum of the number of elements in x plus the number of elements in y. I think even if you didn't learn this, as long as you know what a union is, it's pretty clear, right? If x and y don't overlap at all, then if you want to count how many elements are in their union, then you just add together the number in each set. So use this fact and your responses to A and B to write an equation that relates G to H. So what we can say is since A1H, A2H, A3H, dot dot dot, up through AMH are all disjoint, and the group is equal to the union of all of those. So those all together make up G. What we can say then is that the order of G is just the order of this union, and so we can just get that by just adding the order of all of these together. So each part of the union, we're just adding its order up. And then the order each of these individual orders is just equal to the order of H, right? So what we've really got here is just M times the order of H. Does that make sense to you guys? I hope so. Okay, so part D, explain how your response to part C proves Lagrange's theorem. So we've just directly showed it, that the order of G is equal to M times the order of H, where M is an integer. So this tells us that order of H divides, so there's too many vertical lines in this statement, maybe I should say it with words, divides the order of G. So that's definition of divisibility right there, when the order of G equals an integer times the order of H. Okay, so we did it. Okay, so here is a corollary that we get from Lagrange's theorem. Just to remind you, a corollary is like a little free theorem that you get easily after a larger, harder to prove theorem. So Lagrange's theorem tells us that every subgroup of a finite group must have an order that divides the group order. However, Lagrange's theorem does not guarantee the existence of a subgroup of order M for every divisor M of the group order. Remember that we did have that with cyclic groups, but when you don't know if your group is cyclic, then you don't have a guarantee like that. So the best guarantee that we get along those lines of existence is the following, corollary 26.13. Let G be a group of order n with n greater than 1. Then there is a prime integer p such that G contains a subgroup of order p. So all this corollary guarantees is the existence of some subgroup of prime order p and nothing more. Like, you don't know what p is. Of course you know that p must divide n because of Lagrange's theorem, but you don't know which prime it is if there's more than one that divides n. And so that's pretty frustrating in some sense, but this is the best that we get for general groups. So for example, in a group of order 10, there must be a subgroup of order 2 or order 5, because those are the two primes that divide 10, but you don't know which. It could be both, but you don't know. So let's just look at a brief proof of that corollary, because the proof is pretty short and easy to understand. So again, here is the corollary: let G be a group of order n with n greater than 1. Then there is a prime integer p such that G contains a subgroup of order p. So okay, for our proof, we're going to let G be a group of order n greater than 1 with identity e. Choose an element a, which is not the identity in G. Then we can say that the order of a is greater than 1. And just to remind you, when we talk about the order of an element, that is the order of the cyclic subgroup generated by that element. So this is that. And so the reason we know that's greater than 1 is because that cyclic subgroup would contain A, and it would also contain the identity, and it might contain more, but it would at least contain A and the identity, which is already more than 1. Okay, so anyway, since G is finite, Lagrange's theorem tells us that the order of A, which is equal to the order of the cyclic subgroup generated by A, divides n. And we also know that the order of A must be finite because G is finite. So this is a corollary that only applies to finite groups. They did not note that. Oh, well, I guess they kind of did note it by saying that it was of order n. They didn't specifically say that n couldn't be infinity, but infinity is not a number, so I guess that was sort of assumed. Okay, anyway, so we're working with a finite group. Right, so all of this means that the order of A must divide n, and then the order of A is also finite. So we have that from Lagrange's theorem. So we're going to call the order of A by the name m. So let p be a prime factor of m, and then let k be the integer such that pk equals m. So if p divides m, then of course we're guaranteed that such an integer must exist. That's a definition of divisibility. So then there was this previous theorem back in Investigation 23, that was theorem 23.6, and that tells us the following: that the order of a raised to the k, so that would be the number of elements in the cyclic subgroup generated by a to the k, is given by this formula right here. That was a formula that I believe we actually proved. So the reason that you get that this is equal to m over k here, so this part is coming from that's coming from the theorem. And then the reason that that part equals m over k is because k is a divisor of m. So whenever you take the GCD of a number and its divisor, the GCD will be that divisor. So that's why we get k right here. Okay, so anyway, then we have m over k, and we already said that pk equals m, so m over k is p. And so we got that the order of the element a to the k was p, and that means that the subgroup, the cyclic subgroup generated by a to the k, will be of order p. And since that will be a subgroup of G, then G has this subgroup of order p. So that's it. It's pretty simple. Okay, so let's look at another corollary that is quite useful. So corollary 26.14, let G be a finite group with identity element E, then A raised to the order of the group is equal to E for every A in G. So you take any element in the group and you raise it to the order of the group, then you will get the identity. So the proof here is let G be a finite group of order n with identity element E, and let A be an element of G. Lagrange's theorem shows that the order of A, which is also the order of the cyclic group generated by A, divides n. So there exists an integer m such that the order of A times m is equal to n. It's the definition of divisibility. So then if we take A raised to the n, that will be the same as A raised to the power of A times m. And then we can separate that and rewrite it like that using laws of exponents. And so one of the things we learned, I believe, back in Investigation 23 was that when you raise any element to its own order like that, that you just get the identity. So this identity is coming from this part. Any element raised to its own order will be the identity, and then you have the identity to the m, so that is E. Okay, so now let's talk about the concept of the index of a subgroup. So activity 26.12, that was the one where we proved Lagrange's theorem. That showed us that if M is the number of distinct left cosets of a subgroup H in a finite group M, then M times the order of H is equal to the order of G. And that's just because those cosets, they're all the size of group H, and they partition the group. So this number of distinct left cosets, it actually has its own name, and it's given here in this definition. So definition 26.15, let G be a group and H a subgroup of G. The index of H in G is the number of distinct left cosets of H in G, and it is denoted with this notation right here. So it's square brackets and then G colon H. So notice that when G and H are finite, you can actually calculate this index thing with this formula right here. You just take the order of G and you just divide by the order of H. So that's pretty easy. But the reason why we don't usually give that as the formula for that index, and the reason why it has its own notation, in fact, is because this definition actually applies to both finite and infinite groups and subgroups. So in fact, it's interesting that the index itself can actually be finite, even if G and H are infinite, although that is not guaranteed. You don't necessarily have that it's finite if G and H are infinite, but it's possible. So just to follow on from that, I'll just give you a quick example. So for example, if G is the integers and H is the subgroup 2 times the integers, for example, and that's just 2k for all integers k, then the two cosets that would come from H would just be H itself and then H plus 1. So H plus 1 would give you the odd integers. And so this, so the left cosets here would be H and then 2z plus 1, like that. And so the order, or sorry, the index here of H in G would be 2, because there's only 2 distinct cosets that make up the whole group. So that's an example where both H and G are infinite, but the index is finite. Okay, so let's look at activity 26.16 here. That's going to ask you to calculate some indices. So you can refer back to your answers to activity 26.9, but in fact both G and H in all of these, or in both of these, are finite, so I think it's not too hard to just calculate the order of G and H and then divide. So go ahead and give this a try and then we'll go over it. Okay, so let's go ahead and go over the answers here. So what I'm going to do is I'm just going to calculate what G and what H are in terms of their orders. So the order of G here, it's Z16, so this is going to be 16. And then H, so the subgroup generated by 4, that's going to consist of 4, and then 2 times 4, and then 3 times 4, and then 4 times 4, which is 16, but that's 0. So it's those 4 elements. So the order of H is going to be 4. And so the index here then is going to be just 16 divided by 4, so that's going to be 4. So that 4 there for the index, that means there would be 4 distinct left cosets of H in G that would make up the whole group. Okay, and then for the second one here, the order of this group G, so this is the symmetric group on 3 elements. The number of different ways to rearrange 3 elements is 6, so there are 6 elements in that. And then H, the group generated by this cycle, is just 1, 2, and then if you do 1, 2, cycle 1, 2 times itself, or squared, that will actually give you the identity. So it's just those 2 elements. And so the order of H is going to be 2, and so the index then is going to be 6 divided by 2, which is 3. And so that means there would be 3 distinct cosets made from H that would cover, or that would partition the whole group. Okay, so let's do another activity here. So one thing that, I don't know if you've noticed it so far, but so far all the groups that we've seen that have been of order 2 or of order 3 have been cyclic, but this is not true of the groups of order 4. There are some that are cyclic and some that are not. So one of the things that we can do with Lagrange's theorem is we can actually classify or describe in detail all groups of certain orders, in particular groups of prime order. So let's go ahead and do activity 26.17 here, and go ahead and pause the video and try that, and we'll go over it on the next slide. so let's go ahead and go over this activity. So let G be a group of order P, where P is a prime, and let H be a subgroup of G. What does Lagrange's theorem tell us must be true of H? Okay, so Lagrange's theorem, maybe I'll just call it Lagrange's. Lagrange's tells us that the order of H must divide the order of G. So since the order of G is P, that tells us that the order of H must divide P, but P is a prime, so the only things that are going to divide P are going to be 1 and P itself. So the order of H has to either be 1 or it has to be P. Okay, so what that means is, well, if the order of this subgroup H is 1, then H is just the identity. So I'll call that E, I guess. So the identity. Sometimes we call it I, sometimes we call it 1. So let me just make it clear, I mean the identity. Or if the order of H is P, then H would have to be the group itself. It would have to be the whole group. So what does this mean? This means that G only has these two subgroups. These are the only ones. So the only subgroups of G are just this, what they call the trivial subgroup, the identity subgroup, and then G itself. So G is kind of boring, doesn't have much structure. Okay, so part B, let G be a group of order P, where P is prime, and let A be an element of G. What must be true of the order of A? Explain. Must G be abelian? Must G be cyclic? Explain. And what can we conclude about every group of prime order? Okay, so there's kind of two possibilities here for what A could be. A could either be the identity or it could be not the identity. So let's consider both of those cases. So I'll call case 1 A is the identity. So if A is the identity, then the cyclic subgroup generated by A is just A by itself, the identity. So the order of A would then be 1. Okay, and then in case 2, if A is not the identity, let's call the identity E. Well, then A is in its own cyclic subgroup, and E is also in that cyclic subgroup because it's a subgroup, so it has to contain the identity. So that would mean that the order of A is already at least 2, so it's greater than 1. And we just found in part A that the order of any subgroup of a group of prime order is either 1 or the prime number P itself. So then by part A, the order of A, which is the same as the order of the cyclic subgroup generated by A, would have to be P. Okay? So what that would mean is that actually that cyclic subgroup generated by A that has order P, that has to be all of G. Why? Because there's only these two subgroups of a group of prime order. There's the identity subgroup and the entire group. So if A is a subgroup that is not the identity subgroup, then it must be the whole group. So this is quite interesting because it actually tells us that G is cyclic. Remember that any group is cyclic if it's generated by the, or if it is equal to the cyclic group generated by a single element. So G is cyclic. And now, what can we say about whether G is abelian or not? So since G is equal to the cyclic group generated by A, that means that G consists of just these elements. So there's the identity element, there's A squared, there's A cubed, and there's so on and so forth up through A to the P minus 1. And then if you did A to the P, that would be raising A to its own order, so you get the identity again. So you just have those P different elements, and these all commute with each other. How do I know they commute with each other? Every element raised to any, if you have the same element raised to 2 different powers, for example, and you just multiply them together, that'll always commute because you can just combine the powers. So all of these are going to commute with each other. Oops, I keep messing up my pen. All of which commute. So G is abelian. So this is quite interesting. We found out quite a lot in just a little amount of time about groups that have a prime order. They're cyclic, they're abelian, they only have 2 subgroups. Yeah, so that's pretty great. Okay, so that was the end of Investigation 26. Kind of went out on a high note there. And so let's get started with Investigation 27. We're going to learn about normal subgroups and quotient groups. Quotient groups are quite fun, so I hope that you will enjoy them. Okay, so here's our focus questions. What is a normal subgroup of a group? Why are they important? When is the quotient of a group by a subgroup actually a group itself? What does Cauchy's theorem say about the subgroups that a finite abelian group must have? What is a simple group, and what are some examples of simple groups? Okay, so let's get started with a preview activity, and this one actually involves coloring, so I hope you will enjoy it. So there's a lot of text to start off with here to explain this activity. So recall that if G is a group and H is a subgroup of G, the cosets of H partition G into disjoint equivalence classes. In this activity, we will investigate what these cosets might look like. So the first table up here, this one, this is an operation table for a group G of order 6. Now notice that we're using the first 6 letters of the English alphabet to be the 6 elements, but that does not mean that E is the identity. In fact, E is not the identity. You can figure out which element is the identity if you look at the operation table, and it's actually D. So D is the identity. That's the one that when you multiply by it, it doesn't change what you multiplied by. So the activity here is that we're going to rearrange the elements of G so that the operation table allows us to see the cosets of G more easily. So basically we're going to like group this into like one coset here, and then that's not how you spell coset, I'm sorry. One coset here, and then another coset here, and then another coset down here. So that's how we're going to rearrange them, and then we'll have the same structure up here. Okay, so to start off with, notice that F is an element of order 2 in this group, and the reason for that is because F squared is equal to D, which is the identity. So that cyclic subgroup generated by F, that is just F and D. So we're going to call that cyclic subgroup by the name H. And what we've done here is in the second table here, we've rearranged the table and partly filled it using the elements of H as the first 2 elements in there, so that forms one coset. Okay, so with all that exposition out of the way, hopefully you got the idea of what you're doing. Go ahead and do these 4 parts here, and go ahead and pause the video and try this, and then we'll go over it. Okay, so let's go over this. So we know that H is one left coset of H in G, and now we're going to find the others. So to start off with, we're going to choose another element, little g in big G, that is not in H. In other words, for little g, we're going to use either A, B, C, or E. And we're going to fill in G as the 3rd element in the rearranged table. And we're going to find that coset GH, and we're going to use the other element of GH as the 4th element in the rearranged table. Okay, so I'm just going to make things easy on myself and just make G be A. So I'm going to put that over here in that spot and that spot, and I'm using black here because we do actually have to color in the last part, so I'll do colors at that point. So if little g is A, then little g times H is A times H. So what is A times H? So this is going to be A times the 2 elements of H, which are F and D. So maybe I could write it like this. I'll put A on the outside, and then I'll put F and D in here. And then this is just AF, AD. And so I'm just going to use the operation table to find out what those are. So when I have A on the left and F on the right, that gives me E. So this is going to be E. And then A times D is going to be that is going to be A. I guess I should have predicted that A would be one of these. Okay, so I'm going to get E and A, and so my other element here for the 4th element in the table is going to be E. Okay, so that's my second coset there. So this coset, this was H, and this was GH, and then this over here is also H and GH. Okay, so part B, there are two remaining elements of G that are not in the rearranged table yet. Let G prime be one of them. Fill it in as the fifth element in the rearranged table, then find G prime H and use the other element of G prime H as the sixth element in the rearranged table. Okay, so for G prime, the only elements that I haven't used so far are B and C. So I'm just going to let G prime be B. So then G prime H is going to be BH. So I'm going to write it like this, B times FD, because that's H. So this will be BF and BD. Okay, so BF is going to be C. Okay, and then BD is going to be B, because D is actually the identity. Okay, so we get C and B, and I'm going to fill these in over here. C and B. So this is G prime H, and this is G prime H. Okay. Part C, what is the relationship between H, G, H, and G prime H? I guess I could just say that they partition. They partition G. They have the same order. There's probably some other things we could say. Same order. Yeah. Okay. So for part D, fill in all the products in the operation table. And okay, so let me start by doing that. Fill in all the products. So I know that D is the identity, so I'm just going to quickly do the D row and column first. So this will be F, D, A, E, C, and B. Since that's the identity, I'm just copying them. Okay, and then let's see. So F times A is going to be E, F times E is A, F times C is B, F times B is... This is going to take a while. A times F is E, A times A is B, A times E is C, A times C is F, and then the last one should be D. Okay, so E times F is A, E times A is C, E times E is B, E times C is D, and then the last one is F. Okay, so C times F is B, C times A is F, C times E is D, C times C is A, C times B is E. Okay, and then the last ones I'm going to do by just the Sudoku method. D, what am I missing? It's F, missing E, and then A. Okay. Alright, so that's the whole table there, and now let's do this coloring thing finally. So we're going to color all the cells in the table that correspond to H with blue, those that correspond to GH with red, and those that correspond to G prime H with green. Okay, so let me start with the blue ones for H. So remember that H was F and D, so I'm going to shade in all these F and D cells. So that's F, that's D, F, D. Let's see, where else do I see F and D? Here. There's a lot more problems in math than you might think that are about coloring. You can just study coloring for the rest of your life if you really want to. Okay, so red is going to be for GH. So red was GH, and GH is A and E. So I'm just coloring all the A's and the E's. And then finally G prime H was green. So that is going to be all the rest of them are green. And I want to go ahead and actually do these ones that are on the sides as well. So let me do that. Okay, so let's look at what we've got here and think about what we noticed about this pattern. And I put the hint there, does it remind you of Sudoku? So it should remind you of Sudoku, because what's interesting here is we've got a 3x3 table basically, where we have this blue chunk here, and if we regard that as like a single thing, and this one here, then basically we've got what amounts to an operation table where we're saying that blue times blue equals blue. And then on the other hand, for example, let me use my black to circle it so I'm not messing this up. For example, we have this red block here, and if we multiply this red block here times this blue block here, then we get this red block here. So basically what we're saying is that red times blue equals red. So another example, this green block here, if we multiply this green block times this blue block here, we're getting this green block here, so we're saying that green times blue equals green. So this is quite interesting, right? It really looks like the operation table for a group where your three elements are the three colors, and you can multiply the colors together and get out one of the colors. And it actually is obeying the operation rules for a group where it follows that Sudoku pattern where each element only appears once in each row and column. So if we think of the rows and columns as being like a 3x3 here, like that, then we've got each color block once in each row and each column. And you could even identify, for example, that like the color blue is the identity, because blue times any other color equals the same thing that you multiplied by. So that's quite fascinating. We actually discovered a group by coloring a group operation table. Okay, so let's go ahead and do part E. Okay, so here is part E of the preview activity, and it's just to repeat parts A through D. Don't skip over this though, it is important. So go ahead and give this a try, and then I'll go over it on the next slide. So part E is just to repeat parts A through D for the group operation table that is shown it right there. And this might seem like unnecessary to repeat it, but we're actually going to see something different happen, so it's kind of important that we do it. So let's go ahead and do this part E here. So first we need to find a subgroup H that is of order 2. And I think I'm just going to use A and B for H because I think A and B is a subgroup. First of all, you can see pretty easily that A is the identity. And then you can also see that B times B equals A. So that will be a subgroup right there. It contains inverses, it's closed, it's got the identity, and it's associative. Okay, so H will be our subgroup. So I'm going to call this H here, H, and H. Okay, so I'm going to use the same ordering here that I had up above. So this will be A, B, B, A. Okay, so now I'm going to let G be one of the other elements. So I'm just going to uncreatively choose G to be C. So that will tell me then that GH is going to be CA and CB, which is going to be C and F. So those will be my next two elements here, C and F. And then I'm going to choose my G prime to be one of the elements I haven't seen yet, so either D or E, and I'll just go in alphabetical order and choose D. So then G prime H will be DA and DB. And so let's see, DA is going to be D, and then DB is going to be E. So these will be my last two elements here. So this is going to be, this will be H, this will be GH, and then this will be G prime H. Okay, and so let's fill in the operations here. So the ABC part is the same, so I'm just going to copy that. C, F, and A, and then A is the identity, so I can quickly do those ones too. Okay, so the rest is going to take me a little longer. Okay, so let's see. D, E. So I think actually the only thing that moved out of order was the F column and rows, so I think I can probably use that to go like a little bit slightly faster. So this is going to be F, C, E, D. And then the F one is going to move over here, D, B. Okay, and then the same down here, this is going to be Just have to make sure I'm visually matching this up. So this is going to be E, F, D, B, and then the F1 is going to move up here. So this is going to be C, D. Okay, and then the last little part here. So let's see, DE is going to be moved down there. So DE was A, B, C, F. Oops, it's not an A. A, B, C, F. Okay, and then the F part is, let's see, F times F is E, and then F times D, so this is going to be BA, and then F times, or sorry, D times F is going to be C, and then this is going to be A. Okay, I hope I did that right. All right, so let's do the color coding thing again. So I'm going to do blue for H, so let's color all of the H ones, and this is also H. All right, it's looking good so far. Let's see what else happens. Uh-oh. Uh-oh. This is not giving me that beautiful group pattern, I think. So let's see. Red is going to be for GH. So, okay, it works over here. So that's C and F. But what's happening over here? Oh, C and F, you're not staying together. Oh, no. All right, and then finally our green part. So this is for D and E, and again we're seeing the blocks are not staying together, which is very disappointing. So what you can see here is that you're not able to do that same little color operation table thing where you get that a color times a color equals another color, because for example you have, wait, let me do it with black. For example, you have the red color here, and then you have red color here, but you don't have a solid color block right here. So we don't get the Sudoku pattern on this part. Okay, so now that we've tried the preview activity with quite some fascinating results there, actually, let's get into the meat of this investigation. So let G be a group and let H be a subgroup. So what we saw in preview activity 27.1 seems to indicate that in some cases, the collection of distinct cosets of H and G have themselves actually a group structure. And that was being shown by that coloring exercise that we did. Those colors, those were those were the cosets that were corresponding to the colors. So sometimes they form a group structure and sometimes they don't. So in this investigation, we're going to explore the structure of sets of distinct left cosets, and we're going to talk about when and whether they form a group. Okay, so in order to form a group out of these cosets, we're going to need an operation. So let's talk about how we might make an operation for cosets. So let G be a group with the operation written multiplicatively, H a subgroup of G, and let little g be an element of the group G. Recall that the left coset of H and G containing little g is the set little g H, which is equal to, you just multiply all of the elements in that subgroup H by little g on the left. We will denote by G mod H, which is this right here, G mod H, the collection of all distinct left cosets of the subgroup H in the group G. So just, I put a note here that that's how you read it aloud. G mod H is read G mod H, and that is for reasons that'll become clear later. It does actually have some analogy with modulo n relation. So we want to understand when this set, G mod H, is a group. So when is the set of these left cosets actually a group? So in order to identify a group structure, we're going to need an operation. There's a natural way to define an operation on left cosets, which is the following. So for any two left cosets, we'll call them little AH and little BH, which are in this collection of all left cosets. We can define the product of these two cosets, AH and BH. We can define it like this. We just multiply A and B together and then apply that to the left of H to get another left coset. So that's our operation. Okay, so in this activity here, we're going to address the question of whether this operation is actually well-defined or not. And you might be expecting from that preview activity that we did that sometimes it is and sometimes it isn't. So recall that when we have this relation here, if A is related to B with the tilde H operation, that means that AH is equal to BH, because those are the equivalence classes of that equivalence relation. So in other words, that means that AH can be written in the form BH for any element B that is in that coset. So for any coset, you can pick anything that's in that coset and use it to write the coset. Okay, so you can pick any B that is in AH and use it to write AH as BH. So these ways of writing cosets, they're not unique. And that means that we need to verify that this operation of multiplication of cosets that we made on the last slide, we need to actually verify that regardless of which representatives we use to write the two cosets we're multiplying, that we still get the same product. Okay? So we shouldn't get a different product just because we write a coset with a slightly different looking way of representing it. Okay, so that's what this activity is going to help us figure out. So go ahead and pause the video and try this activity, and then we'll go over the solutions. Okay, so let's go over this activity here. Part A. What would it mean for the multiplication operation on left cosets to be well defined? Be specific. In general, why is it important for operations to be well defined? Okay, so let's get as specific as possible about what it means for this operation to be well defined. And this is referencing the things that I put up here, but you need to like flesh them out a little bit more. Okay, so what we want, so for the coset operation to be well defined, we need the following. So in other words, what we need is that no matter what representative we choose to represent each coset, that we still get the same product. So that means the following. For all, let's call them, I don't want to call them A's or B's, let's call them X's, I guess. I don't know. So for all X in this coset AH, and for all Y's in this other coset BH, and I'm going to multiply these two cosets together. I get the same product from those two cosets no matter which element I use to represent them. So in other words, what we need is that, let me try it like this. We need that AH times BH is the same as XH times YH, which is an alternate way of representing those two cosets. Okay, so this is equivalent to saying that ABH is equal to XYH. Okay, so those two statements there are equivalent. All right, so that's what we're looking for. And in general, why is it important for operations to be well defined? Well, you just don't want to be getting getting different answers when you think you're putting in the same input. You don't want to be getting different output from the same input. So it kind of comes back to the idea of the operation actually being a function of the two things that you're multiplying or the two things that you're adding. You don't want to put in the same thing and get out something different than what you got when you put it in before. I don't know if that's making sense to you. So we need operations to be well defined. Maybe I can just say it like this, so they are predictable. Predictable, understandable, usable, mathematical, all those things. All right, so let's look at part B here. So let G be the 12 element group that is in the table below, and then let H be the set consisting of I, A9, A10, A11, and then K is going to be the set consisting of I, A3, and A4. So it can be shown that K and H are subgroups of G. Fortunately, they're not asking us to show that. Okay, so part I, find the distinct left cosets of H in G, and then what is G mod H? So this might look kind of intimidating to you because it's this huge table, but this is not actually that bad because we can just look at, let's see, where is H? So H is going to be this element, and then also these elements right here. So this together is H. Okay, and then if I want the left cosets of H, all I have to do is look at all of these elements over here and multiply them on the left by the ones that I've circled at the top there for H. So basically, and let me try to do this with a different color. So this is one left coset, and then this is another left coset. Okay, and then we can just keep going like this. This is another one, and so on and so forth. So these are the distinct left cosets. You can just read them off of the table like that. Okay, so let me just list off what they actually are. So I get that I times H, of course, is just H, so that is I, and then A9, A10, A11. Let's see, the next one is when you do A1 times H, and that is A1, A5, A8, and A4. And then we can do A2 times H, and that gives us A2, let's see, A7, A3, and A6. And if you notice, I've already gone through all 12 elements, so that must have been all of the left cosets, because they do partition the group. So if I've already covered all the elements in the group, then that was all of them. So there's only going to be 3. Alright, so now find the right cosets of H in G. How are the left and right cosets related? So we're going to do the same type of thing on the table over here. So let me circle where H is. So H is going to be this, and then also these ones. So that's H. And then, let's see. So for my cosets, they're going to be, my right cosets, let's see. So this will be one of them here. And then another one of them would be here. And then another one of them would be here. And so on and so forth. I think that actually covers all 3 of them, the ones that I just circled. So let's see. So HI is going to be, that'll be just H again. And then if we do, oops, it's on the other side, right? H times A1. That is going to be A1, that's the green one that I circled there, A8, A4, and A5. And then H times A2 is going to be, so A2, and then A6, A7, and A3. Okay, so those are the right cosets. Okay, so how are the left and right cosets of H and G related? So if you look carefully at them, you can see that they are actually the same. So we have that IH equals HI, so that's always the case, of course. But then we also have that A1H equals HA1, and A2H equals HA2. So they're the same. So that's quite interesting. So now let's look at part 3. Find the distinct left cosets of K in G, and then what is G mod K? Oh, I think we forgot to do that on part A, right? So let's actually go back and do that really quick. So G mod H is just simply the set consisting of IH, or just H, I should just call it H by itself, and then A1H, and then A2H. So that's G mod H. Okay, so back to part 3. So find the distinct left cosets of K in G. So K is going to be, so for left cosets we're looking up here, and then let's see, so I and A3 and A4. So that is K. And then so the distinct left cosets, so there's this one, there's this one, And then there's this one, and I think we're going to need 4 of them because there are 12 elements in this set, and this subgroup is only 3 elements. Okay, so let's list those off. So we have just H, or we could also call it, oops, sorry, it's not H, it's K, right? We could call it IK, or it's also just K. So that is I, and then A3 and A4. And then we have A1K, which is A1, A10, and A6. And then we have A2K, which is A2, A8, and A11. And then finally we have A3. Oh, actually we don't have A3K, right? That's not a distinct one. That's one of the ones that we already saw. So let's see, where's the next one that's actually different? I think it's this one. A5, A9, and A7. So A5K is A5, A9, and A7. Okay, so that goes over all of the elements in the whole group, so that must have been all of them. So then we can say that G mod K consists of just K, and then A1K, A2K, and A5K. Okay, so part 4, find the right cosets of K in G, and then what do you notice about the left and right cosets? So the right cosets, so let's see, let me circle K over here. So this is K. And then for the right cosets, let's see, so there's this one, and then there is this one, and then there's this one, and then I'm going to skip the next one because I already saw it, and then, okay, that's also the same, oh, wait a minute. Yeah, that's the same one as before, and then, okay, so the next one that's different is this one. Okay, so those are the 4 right cosets that are actually distinct from each other. So let's see, we start with Ki, which is the same as K, which is just I, A3, A4. Okay, and then we have KA1, which is A1, A11, A7. And then we have KA2, which is A2, A5, and put it over here, A10. And then finally we have KA5, which is A5, A10, and A2. Okay, so what do we notice about the relationship between the left and the right cosets of K and G? So we had that K was the same, but A1K and KA1, they are not the same. So for example, let me just write it like this. A1K is not the same as KA1, and then similarly A2K is not the same as KA2, and so on. Okay, so part 5 here. Give an example to show that the operation of coset multiplication is not well defined on G mod K. Okay, so let's just try doing an example and see whether it is or not for this example. So I'm just going to try doing A1K times A2K, for example. So this is supposed to be A1, A2 times K, which would be A1 times A2 is I. So that's supposed to be just K. And now let's try doing it with 2 different representatives. So let's see, another thing that is in A1K is A6. So I could try doing A6K, and then another thing that's in A2K is A8. So I could try doing this with A8K. Okay, so then I'm getting A6 times A8 times K. So A6 times A8 is A11. So this is giving me A11K. But, so big problem here is that K is not equal to A11K. Those are 2 different cosets. So we multiplied together the same 2 cosets here and here. This is the same. But the answer that we got is not the same. So that's a huge problem. So this operation is not well defined on G mod K. It is well defined on G mod H. It would take a lot of effort to actually show that, since we'd have to try all the different combinations. But we're going to learn more about that next time. Okay, I think we'll leave it there for today, and we'll resume with this investigation next time. So please keep working on your test. Let me know if you need any help with that. Send me an email, and I'll see you guys next time.